Hello class. We're going to review our lessons from sections 2.4, 2.5, and 2.6. So dividing polynomials using the remainder and factor theorem and identifying the zeros and their multiplicities. We'll start by going over division of polynomials, and I'm going to use synthetic division on the majority of these, and actually in all of these examples. So let's go how to set up synthetic division. So we start by first looking at the divisor. And since this divisor is a linear term of 2x plus 1, we're going to write negative 1 over 2. And on the inside, we're going to write the coefficients of 2, negative 13x to the second power, 9x, and the constant 8. Since no power term is missing, less than 3, there's no place to write a 0. No need to write a 0. Now multiplying, bringing down the 2 and multiplying that with negative 1/2, that's equivalent to negative 1. And that adds up now, negative 1 with that negative 13 adds up to negative 14. Multiplying that number with negative 1/2 is positive 7, which adds up to 16. And multiplying 16 by negative 1/2 is negative 8, which then adds up to 0. So here we have a remainder of 0. Now remember, in these situations, because we had a coefficient of 2, and we're writing this negative 1 over 2, we have to then divide these two numbers, or these three numbers, I'm sorry, by 2. So we have to divide every single one of these by 2. And we're going to end up with a total of 1x to the second power minus 7x to the first power, and then my constant of positive 8. So this is the quotient to this division problem. Let's look at example number 2. So we'll start again by setting up our synthetic division. Positive 4, and since the leading coefficient here is 1, positive 4 will be divided by 1, which is still going to just simply be positive 4. Again, no power is missing. We're starting off with x to the third power, and every power is accounted for, so we don't need to put a 0 to hold a place for any of these missing powers. So no missing powers again, like I said. And hold on, this should be 12, not 13. Negative 5, negative 20, and a negative 7. So since the leading coefficient again was 1, we're dividing this over 1. We're going to divide these numbers by 1. So, and only these three numbers, okay, not the remainder. The remainder doesn't get divided. And because, well, since we're dividing by 1, nothing's going to change. The numbers are going to stay the same. So we're going to end up with 2x to the second power. Remember, it's always going to be 1 degree less than the initial polynomial. So our quotient starts with 2x to the second, and then it's a minus 4x to the first power, and then minus 5. A remainder being negative 7 can be written in two ways. We could write it as minus 7 over our divisor of x minus 4, or we can write it as positive 7. We can add the remainder and make the 7 negative. So we could write it again either of those two ways. So like this, or we can write it as plus negative 7. All right, moving on to our next example. We will set this up by first writing a positive 2 on the outside. And since, again, the leading coefficient is 1, it will be 2 over 1, which is just simply 2. On the inside, we start with x to the third power. So the coefficient to that is 3. So 3x to the third plus 4x to the second. But notice that we skip x to the second and our constant. So we're missing an x to the first power. So we're going to use a 0 to hold that place. And then we're going to put the 10 afterwards. So again, every term, every power, every degree has to be accounted for since we less than 3, since we start off with 3. So good strategy to make sure that you have all of your corresponding powers. sorry, I'm trying to grab this. How do I grab this? What's going on here? Here we go. Let me move it down. Since we're starting off with x to the third, we have an x to the second. Notice that there is no x to the first power, and again, the last number, x to the 0 power, which is your constant, is there. So we have every single power accounted for except for this one right here. So that's where we're, again, using a 0 there. And 40, and this adds up to 50. Again, since the leading coefficient was 1, we're dividing the 2 by 1. These numbers get divided by 1. Except for the remainder. Again, the remainder doesn't get divided by 1. But since we're dividing by 1, really, we could just kind of ignore that. And there's your solution. So moving on to the next example, we'll start by writing, again, using synthetic division, we'll start by writing positive 3 over 1. And our coefficients this time start again, our powers start with x to the 4th power. So we have an x to the 4th, x to the 3rd, x to the 2nd, x to the 1st, and then x to the 0 power, which is your constant. We have to have a number for every single one of those powers there. So we have a power, x to the 1st power, and the coefficient for that is an invisible 1, an understood 1. So that starts off with 1. X to the 3rd power has a coefficient of -2. X to the 2nd power isn't on there, so that number is going to be 0. And the coefficient of x to the 1st, that's 3. And x to the 0 power is our constant, is this value right there. So we put 1 there. Now multiplying 1 times 3 and adding that, 1 again times 3 adds up to 3. 1 times 3 is 9, which adds up to 12. And 12 times 3 is 36, plus 1 more is 37. So we're going to start now with 1x to the 3rd power, since the degree of our dividend is x to the 4th. Our quotient would start with x to the 3rd, plus 1x to the 2nd, plus 3x to the 1st, plus my constant, 12, which is 12x to the 0 power, and then again my remainder. Now moving on to example number 5, we'll set this up by writing a positive 5 over 6 and again we have to have every term accounted for. So since we start with x to the 3rd, we need a space for x to the 2nd, x to the 1st, and x to the 0 power. Well, x to the 3rd power, the coefficient for that is 6. X to the 2nd, the coefficient for that is -41. X to the 1st power, coefficient is 60. And x to the 0 power, which is your constant, that coefficient is -25. So bringing down the 6 and then multiplying that by 5 over 6. Let me bring my calculator out for that. So this one I might need a little bit help here. Okay, let's do 6 times 5 over 6. And that's going to give us 5. We add that with -41, and that gives us -36. Let's multiply -36 with, again, that 5 over 6. That's -30. Added with +60. That's +30. And then multiplying that is going to give us 25. Multiplying that 30 with 5 over 6, again, is 25. And 25 plus -25 is equal to 0. So no remainder on this one. Now remember, here then, since we're dividing by 5, by 6, these numbers have to be divided by 6. So we're going to end up with 1x to the second power minus 6x to the first, and then plus 5. That's your quotient. Okay, let's look at the next example. So we'll start by first writing negative 5. We start off with x to the fourth power, x to the second, x to the third. We have to have an x to the second, and x to the first, and x to the 0 power constant. So the coefficient of x to the fourth power, well, that number right here is a 1. So that's 1. The coefficient of x to the third power is 6. The coefficient of x to the second power is also 6. But notice that there is no x to the first power. So we're going to use 0 for that one. And since this one also does not have an x to a 1 power, x to the 0 power, again, no constant, that number is also going to be 0. So bringing down the 1 and multiplying that is negative 5. We get 1 again. So another negative 5. Another 1. Another negative 5, which now adds up to negative 5. Excuse me. And then multiplying negative 5 with negative 5, that's positive 25. So we get a remainder of positive 25. So our solution again, we're going to divide, before I forget, we're going to divide by 1. So dividing these numbers by 1 keeps them the same. And we're going to end up with 1x to the third power plus 1x squared plus 1x to the first power, and then my constant of negative 5 and my remainder of 25 over x plus 5. So here's your quotient. I'm just going to go back and box these in black. Okay. All right, let's go now to the second page, to the back page. And let's now go over the remainder theorem. Now, to use the remainder theorem again, which is referred to as synthetic substitution, we use this again to evaluate the function at C. So here, we want to know what is the output value when x is equal to negative 2. So instead of doing this again using the old and standard substitution of 2 times negative 2 minus to the third power minus 7 times negative 2 plus 3, we're going to use this technique of synthetic substitution. So I set up my synthetic substitution problem, and since I start off with x to the third power, I have to have a x to the second, an x to the first, and an x to the 0 power. I do have a coefficient for x to the third power. That coefficient is 2. So I'm going to start off with 2. I do not have an x to the second power, so I'm going to put 0 for that. The coefficient of x to the first power is this one right here. The coefficient is 7. Oh, I'm sorry, negative 7. And then my constant, my x to the 0 power, the coefficient for that is positive 3. Now the number that I'm going to put outside here is going to be this number here. I do not get the opposite of this value. This number stays the same. So I'll put negative 2 there because I want to evaluate this when x is equal to negative 2. So bringing down the 2, I will multiply 2 with negative 2, add that with 0. Now multiply negative 4 with negative 2, add that with negative 7, and then multiply again 1 with negative 2, and add that with 3, I end up with 1. So the value of f of negative 2, remember, is going to equal to my remainder using this technique. And since the remainder is 1, that is my answer. F of negative 2 equals to positive 1. Now, for the factor theorem, we're going to use the factor theorem and the two given factors here to factor this polynomial completely. Remember that every polynomial can be written as the product of its factorization. So for this example right here, since we have x to the fourth power, I can write this function as the product of four linear factors. So ax plus b, cx plus d, and so on, okay? Qx plus r and hx plus j, for example, okay? So I can multiply four factors to end up again with this polynomial there. Now, I already know two of them. The first two are x minus 5 and x plus 4. It's just figuring out what the other two are, again, because it's a degree 4, figuring out what the other two are, then multiply to give me this entire polynomial. So the way we're going to figure this out, let me erase this, is by using, again, synthetic substitution. So if I divide by these two things, it's going to break this down again into a quadratic, which then I could factor. So let's start by dividing by x minus 5. So I'll write this as a positive 5 since I'm going to divide by x minus 5. So I switch the sign. And since we have x to the fourth power, there has to be x to the third, and x to the second, and x to the first, and then x to the 0 power, your constant. And every single one of these numbers are accounted for. The coefficient of x to the first, since there's no number there, that's understood to be 1. And then the coefficient of x to the third is negative 4, negative 15x to the second, positive 58x to the first, and negative 40x to the 0 power. So we're going to bring our answer down, the first number down, and we start multiplying and adding. I'm sorry, that's positive 8. And 0. Now, if you do not get 0, again, because this is a factor, I'm supposed to get 0. And then if you do not get 0, then there was a mistake again in your multiplication and adding. So go back and check. Now, since we also know that x plus 4 is also a factor, that means it's going to divide this. But since we now have a quotient to dividing by x minus 5, I can also verify by dividing this. So instead of using this and doing it all over, we're going to use our answer and divide by x plus 4. So we're going to put negative 4 on the outside and multiply and add. Multiply, add, multiply, and again add, and we get 0 like we're supposed to, because again, this is a factor, so our remainder should always be 0. Now as a result, we now have x squared minus 3x plus 2, and we want to factor this. And because it's a quadratic, we can now do that. So again, what we're trying to do here again is to figure out the factors of 1 times 2, which is 2, that is going to add up to negative 3. So what two numbers multiply to give us 2 that add up to negative 3? Well, since 2 is a prime number, there's only one possibility, 1 times 2. That's the only way to multiply to get a 2. Now we need these numbers to add up to a negative 3. So a positive 1 plus a positive 2 does not add up to a positive 3. But if I make them both negative, they do. A negative 1 plus a negative 2 adds up to negative 3. And they also, again, because they're two negatives, they multiply to a positive 2 as well. So that satisfies my factors. We have x minus 1 and x minus 2. Now, since the leading coefficient, again, was 1, dividing these two numbers by 1 is going to keep it the same. So my complete factorization is going to be the following. So again, given that we have these two factors, and we just found out these two new factors. This is the complete factorization of f of x. So I can write f of x as x minus 5 times x plus 4 times x minus 1 and x minus 2. So these are the four things that multiply to give us again this polynomial here. So on tomorrow's quiz, this again is the expectation for you to identify, and thus not the remaining two factors, but again to simply write the function as the product of it all of its factors. Okay, moving on now to the zeros. So to find the zeros, again, we have to factor the polynomial. So here we have two polynomials that are already factored for us. And the way we find the zeros is by setting these things again equal to 0. So what makes x equal to 0? Well, that would be 0. What would make 2x plus 3 equal to 0? That would be negative 3 divided by 2. And what makes x minus 4 equal to 0? Well, x would have to equal to positive 4. So those are our zeros. So our zeros are those three values. Now for number 10, same idea. What's going to find the zeros, we're trying to solve this equation. So what's going to make each one of these factors equal to 0? Well, for the first one, x would have to be negative 3. For the second factor, x would have to equal 2 over 3, positive 2 over 3. And for the third factor, x will have to equal positive 3. So those are your zeros. Negative 3, positive 2 over 3, and positive 3. Now on numbers 11 and 12, you have to identify the zeros and their multiplicity. So for number 11, our zeros are whenever we touch the x-axis, our x-intercepts. So in this situation, there's 3 of them. And their multiplicity is going to be the number of times that x will equal to. So here we have that x equals to negative 3, x equals negative 1, and x equals positive 2. And their multiplicity is going to be the number of times x can equal each one of these values. Well, we're not going to determine, again, the exact number. We're going to determine whether that number is going to be an even or odd value. So how many times can x equal to negative 3? Well, because it crosses the x-axis and actually crosses through, that means it's going to equal to negative 3 an odd number of times. So x equals negative 3, 1, 3, 5, 7, 9 times possibly. And like I said, we're not going to identify the exact number of times, just their multiplicity as an even or odd possible value. So in this situation, x can equal to negative 3 an odd number of times. At negative 1 and at negative 2, because it touches, it's tangent to the x-axis and simply just touches and bounces off the x-axis and not actually crosses through, then that means that x equals to negative 1 and positive 2 an even number of times. So maybe 2 or 4 or 6. But again, we're not going to go into actually identifying what that value is, just simply be able to understand that has to be an even number of times. So the multiplicity would be even. Now let's look at the next example. So for the next example, our zeros are going to be these three values when we intercept or actually touch the x-axis. So x equals negative 2, x equals positive 1, and x equals 3. And well, what are their respective multiplicities? Well, at negative 2, since we actually cross through, the multiplicity has to be some odd number. So x equals negative 2 an odd number of times. So like 1, 3, 5, etc. And the same thing at 1. Since we actually cross the x-axis at 1, this polynomial will equal to 1, also an odd number of times. And at 3, since the graph simply touches and bounces off, that means that x is going to equal 3 an even number of times. So possibly 2 or 4, more than likely probably 2 because of the number of times it turns. It has 1 and 2 turning points. So it has to be at least a degree 3, okay? So maybe these are going to be 1, 1, and this is 2, or it's going to be a little bit higher than that. But it has to be, again, higher than that. Higher than 3 times. Sorry, 4. 1, 2, 3. There's 4 turning points. So it has to be a degree 4. Well, there you have it, okay? So that concludes, again, the review for the quiz on this next 3 sections. If you have any questions, please send me a message on Remind or through email. I appreciate you watching, and I hope you have a great day. Oh, one last thing. Do not forget, again, to submit these answers, again, on EdgeElastic. On EdgeElastic, again, remember, I count this as a grade. So again, thank you again for watching, and I hope you have a great day.